All right, Gen Chem, we are going to start a new chapter today. So we are going to start learning about solutions and mixtures and their properties. So first, we're going to start off with some vocab words. And we had these vocab words at the beginning of the year when we learned how to classify materials. We learned how to classify materials into pure substances and mixtures. So now we're going to talk about mixtures. So let's go over some of these vocab words. So hopefully, it's been about 6 months since we've done them. Hopefully you remember some of them and it's kind of review. Okay, so our first one that we want to define is a solution. If you remember, a solution is a homogeneous mixture, which means that that mixture is uniform throughout that mixture. So let's write that down. Homogeneous mixture. Okay, so it is uniform throughout the mixture. Now, to get a uniform mixture throughout that mixture, what that means is our particle size has to be down to about the atom or the molecule size. So let's write that down as well. So particles are down to the atom or the molecule size. So we have things dissolved down to individual atoms or individual molecules. So we're very, very tiny particles. That's how we get that uniformity. All right, solvent. Let's define that. Now, solvent is what we dissolve things in. So it is what does the dissolving. What we dissolve things in. So, for example, if I took a spoonful of sugar and put it in a cup of water, the solvent would be water. So solvent, when we're talking about solutions, it's always the majority portion. Okay? Now, solute is kind of the opposite of that. Okay? So solute is what gets dissolved. Okay? What gets dissolved. So in my example of sugar water, sugar would be the solute. Water, of course, is the solvent. So solute is always, when we are talking about a solution, the minority portion. Or the smaller portion of that mixture. Okay? And then we have a couple of other definitions of mixtures, but these are not uniform. So these are, let's set this aside. These are heterogeneous. So heterogeneous means they are not uniform. So we have little bits and chunks in there that we can actually see that aren't uniform. So a good example would be a chocolate chip cookie. We've got little bits and chunks of chocolate chip stuck in the middle of the dough. And that chocolate chip distribution is not uniform throughout a chocolate chip cookie. Okay, so suspension is a heterogeneous mixture so we're going to just put heterogeneous on here again, where the particle size is large enough that the particles, if I don't agitate or stir that mixture, the particles will fall out of solution. Enough so that particles will fall out of the mixture without agitation. Agitation is just a fancy word for saying stirring, shaking, some kind of mixing. So a good example of this would be sand and water. So if I put sand and water together, if I don't shake up or stir up that mixture of sand and water, if I let that sit still for a minute or two, that sand is going to come out of solution, and you'll find a bunch of sand on the bottom of the bucket or the bottle or whatever I've put it in. Okay, so suspension means that we can have large enough particles where if I don't keep this stuff stirred up, you're going to fall out of that mixture. Okay? Colloid, though, is definitely heterogeneous still. I love how the ink color changes as I'm writing. So heterogeneous, but the particle size is medium size. So we're not so large that we'll fall out of the mixture if I don't stir, but we're not so small to be down to the atom or the molecule size. So the particle size is medium, like in the middle. Okay? So that when the mixture is not agitated. Now remember, agitated is just a fancy word for shaken, stirred, some kind of disturbance. So when that mixture is not agitated, or if I let that mixture stay still, the particles don't fall out of solutions. Or not solution, the mixture. The particles do not settle out. Okay, so a good example of a colloid would be lotion, for example. I've got some lotion right here. This is a mixture of some oil or some kind of fat with water. Normally it separates, but we've whipped it up so that the oil particles are small enough that they are whipped into that liquid water and they stay in the mixture and they don't separate out. So I can use this pump of lotion and still get lotion out instead of getting a glop of water sometime and a glop of oil sometime. Okay, so we can make these kind of colloids mixtures by whipping or making those particles really, really small. Okay, and I still have no idea why that just flipped on me, because I didn't even move my mouse. Okay, so let's find where we're at. Okay, now let me talk about solutions really quick and mixtures. A lot of times people think that solutions have to have a liquid part of them to make a mixture. They don't. So I can make a solution with air. So let's give some examples. So solution, air is a solution. Oh my, why did it do that? Okay, let's get back here. Okay, air. Okay, so air is a really good example of a solution because we have a mixture down to the molecular level of nitrogen and oxygen and a whole bunch of other gases mixed in there. Now, could you imagine if this was not uniform? You would walk through pockets of just nitrogen and you wouldn't be able to breathe. And then we'd walk through pockets of just oxygen where the explosive and combustion capabilities would be so deadly that that wouldn't be good either. So it's a good thing that it is a uniform mixture so that we can breathe pretty much wherever we go within the atmosphere. As long as we stay down below about 10,000 meters, we can breathe pretty well. Okay. Another solution that most people don't think is a solution would be an alloy. I don't know if you guys have ever heard of the word alloy, but it's a solution of two metals that are mixed together. So it's a solution of two or more metals. Sometimes we don't even use metals. Sometimes, for example, steel is a mixture of iron and carbon. And adding that carbon in there uniformly in that iron mixture, steel mixture, makes it so much stronger. That's why we use steel to build things instead of just plain iron. Okay? So mixtures and solutions don't have to just be liquids. They can be a mixture of liquids and solids like salt and water. They can be a mixture of gases. They can be a mixtures of solids and solids like alloys. We can have all kinds of different mixtures. Okay? All right, let's go into why water dissolves table salt so well. So here is our model of table salt. And we've seen table salt. Hopefully you paid attention when you sprinkle it out on your hand or on your food. You'll see these perfect little cubes. And these perfect little cubes are this crystalline structure. Do you see that perfect little cube there that I just drew in? It's the crystalline structure of the sodium ions, which are these little gray ones, and the chloride ions, which are the big green ones. Now, if you remember, table salt, NaCl, is made from sodium that has lost one electron and become a sodium plus one ion to get the noble gas configuration of neon, and chloride ions, which have gained an extra electron and now have a charge of -1 to have the noble gas configuration of argon. Okay? That's all the way back to first quarter, if you remember all the way back. So, and then we're going to pair in our Lewis structure of water. So if we dissolve things in water, if you remember, water had kind of this bent shape because we had two lone pairs of electrons on there. And we have a huge electronegativity difference between oxygen and water. So oxygen has an electronegativity of about 3.5, and hydrogen has an electronegativity of about 2.2, which gives us a difference of about 1.3. And we also have oxygen bound to hydrogen, which gives us hydrogen bonding, which makes that electron pull of the oxygen even stronger. Okay? So that means that the oxygen end is going to be pretty dang negative. Okay? It's going to pull those electrons towards it, plus it has those two pairs of electrons. That means that the hydrogens almost don't have their electrons at all. They're almost full +1 charges. So that means our hydrogen end of the water is going to be very positively charged, and our oxygen end of the water is going to be very negatively charged. Okay? So you grew up, hopefully, playing with magnets, and hopefully you remember that magnets attract each other. And if you remember correctly, the positive end of a magnet is going to attract the negative end of another magnet. So because sodium chloride has a positive end, could it be attracted by the negative end of the water? Yeah. So let's look at what happens. Water, as you see in this diagram, is a relatively small molecule. It's so small that it can actually kind of fit in between sodium and chloride a little bit. And if I can wedge enough waters with the oxygen ends towards those sodiums, I can wedge it and pull that sodium out, away, and surround it by water molecules with the oxygens all pointed inside toward that positive sodium. So the negative oxygens are going to surround that positive sodium. Opposites attract. And on the flip side, I can get the tiny little waters on the oxygen ends to come in, or on the hydrogen ends to come in and surround a chloride ion like this. And if I get enough of them to come in and surround a chloride ion, they can also pull the chloride ions away also and surround them with the positive ends of these hydrogens towards the negative chloride ions. So if I get enough of these water molecules to come in and do that, I can actually dissolve the salt. And that's what happens when we stir things up and we dissolve salt when we're making stuff. Okay? So remember that water here, we are right here. Remember, when we look at water's Lewis structure, water is polar. It has the negative oxygen end and it has the positive hydrogen end. So it is a polar molecule. It has a positive pole and a negative pole. Okay, so it has a positive end and a negative end. Okay, salt also has a positive end. Remember, that is the sodium ion, and the positive end of water is the hydrogen, and the negative is the oxygen. Okay, and salt also has a negative end. It's the chloride ion. Okay, now opposites attract. So opposite, the hydrogen end of water can go and attract the chloride end, and the oxygen end of water can go in and attract the sodium end. So water can dissolve other compounds that also have a positive end and negative ends. So basically, water can dissolve polar things or ionic things. As long as I have poles, positive and negative ends, water can get in there and dissolve there. But water cannot dissolve things that do not have a positive end or a negative end. Because if I don't have poles on that molecule, there's nothing on that molecule for water to be attracted to. Okay? So water cannot dissolve things that do not have a positive and a negative end. Because there is nothing on nonpolar molecules for water to be attracted to. Well, it doesn't need two O's, it just needs one O. It's not that kind of a two. Okay? So, let's look at the Lewis structure for carbon tetrachloride. Okay, I'm going to draw it over here. So if I do carbon tetrachloride, okay, there are my four chlorides around my carbon. So the chlorines are going to have 3 lone pairs on them to complete the Lewis structure. Okay, now this is a tetrahedral shape. And yes, there is a dipole difference between carbon and chlorine. So carbon has an electronegativity of about 2.5, and chlorine has an electronegativity of about 3.1. So that gives us a difference of about 0.6. which we would say is definitely polar. But if we look at all of these dipoles and we look at how they react, doesn't that one cancel out that one? And doesn't this one cancel out this one? So those dipoles all cancel. And because those dipoles all cancel, carbon tetrachloride is non-polar. Okay, so it doesn't have positive or negative ends at all. So carbon tetrachloride is nonpolar. And because it is nonpolar, it doesn't have ends that are positive or negative, and therefore it cannot attract other molecules that have positive or negative ends. So it can't dissolve polar or ionic solutes because polar and ionic solutes have poles. They have positive ends and negative ends. But it can dissolve nonpolar solutes. So things that do not have poles, that have equal electronegativity all around it, nonpolar things can dissolve that. So here is our general rule for solubility. Like dissolves like. So what does that mean? So let's change our color really quick. So that means that polar things will dissolve polar things. Polar will dissolve polar or ionic substances. Okay, so if I want something to dissolve something that is polar or ionic, I better have a polar solvent to dissolve it. Nonpolar solvents, and I should also put solvents in here. Nonpolar solvents will dissolve nonpolar solutes or substances. Okay, so how many of you guys have taken, have accidentally got your gum stuck in your hair when you were a little kid, or in carpet or in your clothes? How many of you guys were successful in getting it out of your hair? Does gum dissolve with water? No, because gum is nonpolar. So to dissolve gum, you're going to also need a nonpolar solute. So how many of your parents knew the trick to use peanut butter or some kind of oil to get that gum out of your hair without cutting your hair? See, chemistry can be useful. All right, let's think about saturated, unsaturated, and supersaturated. Okay, when I think of something that is saturated, we sometimes, especially in art, we use the word saturated to say that it's full of color. We can't put any more color in there. Or sometimes we think of it as being able to absorb something. If something cannot absorb some more stuff, if I have a sponge that's completely full of water and it can't absorb another drop of water, that sponge is saturated. Okay? So when we have mixtures, we can only put so much solute in there before it can't dissolve anymore. So a saturated solution has dissolved all the solute that it can at that temperature. So it is a solution that has dissolved as much solute as possible. at a given temperature. Okay, so for example, if I put a teaspoon of sugar in water and stirred it up, I would expect that to dissolve. But if I kept doing that, I would eventually get to a point where I cannot dissolve any more sugar. Keep putting in more sugar. So if I put in yet another teaspoon after I've reached the maximum that it would dissolve, that last teaspoon wouldn't dissolve. I'd still have sugar on the bottom. So a saturated solution has dissolved all it can at that temperature that you have the solution at. So if that's saturated, what does unsaturated mean? Okay, un means not, right? So if it's unsaturated, it is a solution that has not dissolved as much as it can. So a solution that has not dissolved as much solute as possible at a given temperature. So I would still be able to dissolve more in an unsaturated solution. I could still put more solute in there and expect it to dissolve. Now, supersaturated. Super. This is coming from the German usage of super. Super means above and beyond. So if it's supersaturated, super means it's saturated, it's got more solute than it normally possibly can. So it's above or beyond saturated. So this is a solution that has dissolved more solute than is normally possible. At a given temperature. So you're probably wondering, how do I get more solute in there than is normally possible? Now, if you've ever heated stuff up, and if you've ever made, hopefully, I don't know if any of you guys have made candy before, but if you make candy, you're taking a solution of sugar and water and you're heating it up and boiling that so that you can get even more sugar in there. And then you cool it down so that that sugar stays in that solution. And you usually cool it down to the point that you can make either hard candy or rock candy or something like that. So if I heat it up and then cool it down gradually without disturbing that solution, I can usually keep that extra solute in solution. If I disturb that solution by putting a crystal in it for it to start crystallizing on, or I bump it and give it a shock wave for it to start crystallizing on, or some dirt or something, it will start to crystallize. And all that extra solute is going to come out of solution. I've attached a demo of a supersaturated solution for you to watch. So make sure that you watch that demo. It's in this module. Okay, we're going to look at the effect of temperature on solubility. So let's look at this graph here really quick. So here on the x-axis, we have temperature. And notice that the temperature as we travel from left to right is going up. And notice as we go on the y-axis, it is the number of grams per 100 grams of water that I can dissolve. That this is the solubility line that I can dissolve in that. So if we look at the slope of all of these lines, notice as the temperature goes up, the solubility goes up. Now, does it go up uniformly for all these different compounds? No. But the general trend is as the temperature of the water goes up, the more solute or the more things that I can dissolve in that water. Okay, so let's put down that general trend. So I do not want my highlighter. As the temperature increases, right? As the temperature increases, the solubility of most substances also increases. Warmer water or warmer solvent allows you to dissolve more things. How many of you guys have ever tried to wash dishes with cold water? Does it work very well, even with soap? No, it doesn't. Even with soap, if you really want to get those dishes clean and get all that stuff off the dishes and into the water, you have to have warm water, even hot water, to get those dishes clean because solubility of stuff increases when the water is warmer. Okay, so that is the general trend. Okay, so we are going to leave it at that today. You have an assignment attached in this module as well. I hope you have a great day. We'll see you later. Bye.